give you today over this stuff is not going to be due until Monday as well. But we'll probably spend quite a few days on this concept because it's very important. I think there's some notation within it that at first exposure to gets kind of confusing. So we'll try to make sure that we see it as much as we can. We're talking about compound inequalities. Okay, what is a, just going off of English, what's a compound word?
Two words that come
What?
Two words that come together to make one word, right?
Yep.
So like
Yep.
bookshelf, right? Okay, or classroom, something like that, right? Fingerprint. Is that what you said?
Yep.
Okay. So compound inequalities is the same idea. It's two inequalities that come together to make essentially one inequality, okay, or one statement, okay. So a compound inequality, by definition, is an inequality statement that consists of two distinct inequalities joined by the word and or the word or, okay. Now, if I say you have to be, let's see here. I think of an analogy here. Let's say you have to be. Let's say we're going to divide the class up into groups, and I say you to be in group 1, you have to be a male and have blue eyes. You have to have both of those pieces of criteria met before you get in that group, right? Make sense? Okay. If I said you have to be a male or have blue eyes, you only have to have one of those things, right?
Yep.
So in that group that is made, could have boys in it that have all colored eyes, right? Or it could have girls in it that just have blue eyes. Does that make sense? Okay. So the idea of or means that we can meet one of the two conditions that are provided. The idea of and means we need to meet both conditions provided. Okay. So that's something to think about. That's going to be kind of the basis of this discussion that we have here. Okay. The first thing we're talking about is the graph of a compound inequality with the word and in it. Contains what we call the overlap of the graphs of the two inequalities. Okay? So when we do compound inequalities, we'll only ever deal with two at a time. Okay? At least right now. We get in geometry, maybe we do 3 and 4 and that kind of thing, but right now it's going to deal with 2. If they have the word and, we're going to graphically look for the overlap of what those two statements are. Okay? Sometimes this word overlap is replaced with the word intersection. Okay? Sometimes the word and is replaced with the intersection. Okay? So we might say graph x, the intersection of x is greater than or equal to 3 and x is less than or equal to 7, something like that. Okay? But the word intersection or overlap is what we're looking for here. Okay? It says the reason for this is that our solutions of our graph will satisfy. Remember that phrase satisfy just says makes true the first inequality and the second inequality. Okay? So if I look at that statement that says graph x is greater than or equal to 3 and x is less than or equal to 7, the things that show up in that list of numbers in the end as a solution are kind of analogous to that group of people that were male and had blue eyes. They have to have both those conditions. Does that make sense? So to be in our solutions up there for that particular problem, the numbers need to be bigger than or equal to 3 and they have to be less than 7. Does that make sense? So give me a number. Any number you want to.
4.
Okay, 4. Is 4 bigger than or equal to 3? Okay, so it's bigger than 3. So it works for that one, right? Okay. is 4 less than or equal to 7? Yes. So it works for that one, right? So 4 satisfies both of those conditions, both those inequalities. So 4 better be part of our overall answer. Does that make sense? Let's talk about like the number 12. Okay? Is 12 greater than or equal to 3? Yes, it is. Okay? Okay? Is 12 less than or equal to 7?
No.
No. Okay? So do you see how 12 did not work for both of those? So 12 better not be in our answer. Does that make sense? Okay? So for things to be in our final answer, they need to satisfy or work for both of those inequalities. All right, so this is how we do this graph. It's not too bad. And eventually what we'll do is maybe try to come up with some ways of maybe cleaning this up, making it a little bit simpler. But a lot of times I think the best thing to do for us is to look at the individual components. Look at x is greater or equal to 3. So let's graph x is greater or equal to 3. Okay? I'm going to graph that on this first line here. X is greater than or equal to 3. Actually, I'm going to write that over here. If x is greater or equal to 3, what kind of dot do I use? Close dot. At what number? 3. And now, greater than or equal to would mean change which direction? Right. All right. All right, so that is x is greater than or equal to 3. Everybody agree with that? Yes. Okay. Let's look at the second one. So x is less than or equal to 7. Okay. Now I go to 7. And what kind of dot do I use? Close dot. And we're shade to the left. So those would be all the values that are less than or equal to 7, right? Okay. Now, there's only a few values. I won't say a few. There's actually an infinite, but there's only some of those values that are up there that will work for both x is greater than or equal to 3 and x is less than or equal to 7. And the ones that work are when we take those two graphs right there and we merge them together. We make them kind of lay on top of each other. Does that make sense? And look at where they overlap. If we were to merge these on top of one another, would you guys agree that they start to overlap right there at 3? Okay? So you're going to put a closed dot here at 3. Would you agree that they also kind of stop overlapping after 7? So put a closed dot on 7. Do they overlap everywhere in between 3 and 7? So the idea is that I should have a dot. They overlap here. I should have a dot there. They overlap at 4. I should have a dot there. I should have a dot everywhere between 3 and 4. So what I end up doing is that they overlap between 3 and 7. So I shade that. That right there, folks, that blue line, that we call that a segment, that blue segment is the set of values that is represented by this statement that x is greater than or equal to 3 and x is less than or equal to 7. You first told me 4, didn't you? Is 4 in there?
Yeah.
Is 5 in there?
Yes.
Is 6 in there? If all those values satisfy that first one, x is greater than or equal to 3, and the one being less than 7, less than or equal to 7. Now, does 8 work?
No.
No, 8 only works for this one here, right? 8 is only bigger than or equal to 3, but it's not less than or equal to 7, so it should not be in my final answer. So we're looking for the overlap when we see the word and. Is that okay? Okay. There's going to be another way that we can kind of see this statement here a little bit. Okay. And I'll keep that until I think it's maybe the second page or third page on there. We'll get to that. Okay. But the other option is to see the graph of a compound inequality that uses the word or. Okay? So or means basically we are going to graph our solution, and whatever is graphed as solution, we should be able to pick one of those numbers off, and it will work for one or the other inequality. Okay, so I don't know why I didn't write down an inequality here, but this is what you're going to see. Let's do an example. Let's say that we've got x is greater than or equal to 6, or x is less than 4. Okay? So OR says that we're going to it says the graph of compound inequalities, the word OR contains each graph of the two inequalities that form the compound inequality. So this last graph here that we make, this third graph, is just going to be everything that we graphed in the first graph, along with everything that we graphed in the second. Okay, so we're going to kind of merge it together, and when they merge together, we're going to graph everything that is visible to us. Okay, and the reason for that is that we want solutions that will work for one or the other inequality. So let's say, like we did in the last, let's graph x is greater than or equal to 6. If x is greater or equal to 6, what kind of dot do I use? Closed dot. Okay, so that's 6. And we're going to shade which direction? To the right. Okay. So if x is greater than or equal to 6, now I'm going to do x is less than 4. So less than 4, what kind of dot do I use? Good. Shade which direction? Shade left. Okay. So the word OR here then says when I graph x is greater than or equal to 6, or I graph x is less than 4, the solution to that is everything that you graph in the first graph. So you're going to graph this thing again. And then it's everything that you graphed in this one. Okay. So that last graph then is our final answer. And here is the argument. Okay. Let's pick a number off.
5.
Okay. Well, let's actually do one that works first.
3.
So let's try 3. Okay. So if I plug 3 in here, is 3 bigger than or equal to 6? No. Or is 3 less than 4?
Yes.
Yes. So we want a yes for at least one of those. Does that make sense? When it was an AND statement, we wanted yes on both of them, correct? An OR statement, we only needed a yes on one of them. Okay? So if I tried 7, okay, is 7 greater than or equal to 6? Yep. If I put 7 here, is 7 less than 4? Nope. Well, what was I looking for? Just my one yes, right? Now, if we go to 5, or even if we go to 4, let's go to 5 first. If I say 5, is 5 greater than or equal to 6? Nope. Is 5 less than 4? Nope. So because they both said no there, that should confirm why we don't have a graph. We don't have 5 shaded in red down there on the bottom graph. Okay? Now if I tried 4, just think about this. If I tried 4 in here, is 4 greater than or equal to 6? Nope. Is 4 less than 4? Nope. They're equal, right? Okay. So that's why there's an open dot there at 4. Okay. It means it's really not a solution. It means 3.9 repeating is a solution, but 4 is not. So that's how we do ORs. Okay. So and is the overlap, or is it's everything. Okay. It's both graphs, all of both graphs. Okay. So let's do a couple examples here. So your first handful of questions in your homework will not actually give you algebraic inequalities. They're going to give you verbal phrases. Okay. So I'm looking at all real numbers. So we use whatever variable you want to. I'm going to say n. Okay, so it's all real numbers that are greater than -2. So does that mean n is greater than -2 like that? Like that? And less than 6. So n is also less than 6. And that word and means we're going to need the overlap, right? Okay. It might be a good idea, guys, as you're writing these down, you're doing homework, when you see the word and, you write down overlap. And that should help then kind of realize what we need to do here. So then we're going to n is greater than -2. I'm going to graph that one. So at -2, is that an open or closed dot? Open. In which direction do you shade? Right. Okay. Now on the next one it says n is less than 6. What kind of dot do I use at 6? Open. Open. You shade which direction? To the left. Okay, let me shade you kind of thing here. Okay, so now when we say and, okay, so this is going to be n is greater than -2 and n is less than 6. We're looking for the what of those two graphs? Where they overlap, right? Okay. What number do they start overlapping at? Okay. So -2 right here, we start to see them both being graphed, right? Now think about this. When I have an open dot right here at -2, it really means the last number that I'm going to include in this list, I guess it would be the first number I include in this list, is 1.99 repeating forever. Does that make sense? -2 really isn't in there. Does that make sense? So do both those graphs have -2 in them?
No.
No.
They do.
No, they don't.
Look.
The top one has an open dot at -2.
Oh.
That means -1.9 repeats forever is the first number to start that list. So the overlap starts at -1.9 repeating forever. Does that make sense? So the overlap starts at -1.9 repeats forever. Well, can I find -1.9 repeating forever on my number line? Can't find it, right? So what do? We go to -2, and we will put what kind of dot?
Open.
Open dot. Okay? So we do kind of see that they both get or at least the first one starts at -2 with an open dot. The one below it has its graph at -2, but it's a closed dot. In this case, when we do the overlap, if there was an open dot in one of those graphs, we use the open dot in the overlap. Okay? Because remember, it has to be in both. -2 has to be in both those, and it's not in both of them. It's only in the middle one. Okay, this one here does not exist up here. Does 6 exist in both these?
Yeah.
Is 6 in this one here?
No.
No, that one's open, right? So 5.999999, right there, 5.9 repeating forever is the last number that's included here. Okay? So to actually express that 5.9 number forever, 5.9 forever, we have an open dot at 6. Does that make sense? Okay? Now, would you agree that they overlap everywhere in between? Okay, so then we're going to shade in between those two things. And what that does, I'm just going to check some answers here. Give me a number off that number line.
3.
Okay, so 3. I'll plug 3 in. Right here is 3 bigger than -2. Yes? Is 3 less than 6? Yes. So that's why 3 should be graphed. Let's say -2. Let's try -2. If I plug -2 in right here, is -2 less than 6? Yes. Is -2 greater than -2?
No.
No. And remember, we need 2 yeses for it to be graphed down here, right? So that's why it's an open dot right there, because it didn't satisfy both of these. It only worked for one of them. Okay? If it was a closed dot here, if that was closed, then this would be closed, and then -2 would work for both of them. Yes. What if I chose a number like -6? Is -6 greater than -2? No. Is -6 less than 6? Yes, but I need 2 yeses, right? And right there, I'm getting a yes and a no, so that's why down in that blue graph at the bottom, -6 is not graphed in blue. All right? What we need to understand here is that those blue solutions are going to be, they will work for both n is greater than -2 and n is less than 6. Those blue solutions meet both those conditions. Now, when I say these blue solutions, are there only 1, 2, 3, 4, 5, 6, 7 solutions? Are -1, 0, 1, 2, 3, 4, and 5 the only solutions that work?
No.
What other numbers work?
Decimal fraction.
Okay, decimal fraction. And even numbers like pi are up there, square root of 2, so there's irrational numbers up there. There's actually an infinite number of values there. Does that make sense? Okay. You give me 2 points on the number line, no matter how close or how far apart they are, there's always going to be an infinite number of numbers between them. Okay. And that's the idea. Okay. -2 and 6 are 8 units apart from each other, but there's not 8 solutions there. There's an infinite number of solutions there. All right. Does that kind of make sense? All right. Let's go to this one. It's all real numbers less than -3. So how do I write that? All real numbers less than -3.
I'll go to circle.
Well, give me your variable.
Oh,
Variable.
oh,
And less than -3 would be that, right? Does that make sense? Or, okay, so it says or, your real numbers, so your n again, is greater than or equal to 2, okay? So now, if I'm going to graph n is less than -3, what kind of circle? Annika, what kind of circle?
open.
Open.
And then to the left.
You can't do it. You're all sassy. You answered the question 4 times before I asked it. And then I asked it, you didn't answer it.
No, I did.
All right, so n is less than -3 gives you this, right? N is greater or equal to, what kind of graph is that? What kind of dot do I use there? Close. So n is greater or equal to, close dot, and now shade to the right. Okay. Now, if I ask what does n less than -3 or n greater or equal to, looks like we're graphing that whole thing. Okay. What's the word or mean to us?
One or another.
Okay, so my answers have to, the answers that I take off have to match one or the other of those inequalities, right? So that means in regards to these 2 graphs, I'm going to graph everything. I'll graph everything from that one along with everything from that one. So I'm going to go to, I got to close this and start it back up real quick. My selection tool won't work. There we go. All right, so I'm going to do all of this one. So it'd be -3, graph that way. And I'm going to do all of the second one. So it'd be 2, graph that way. Okay. Now the idea is any number that is ticked off of the blue, we call those rays, anything ticked off those blue rays, any number will work for one or the other of those inequalities up there. Does that make sense? Okay, it's a solution for one or the other. the next question here, guys, it says compound inequalities that require you to solve first. These should be things that we already know how to do. Okay, we're just going one step further now. We're combining what we did yesterday, day before, with what we just learned. So what I want you guys to do on your own real quick, solve that inequality all by itself. Once you get that one solved, solve this one by itself. So solve the blue one and the yellow one, all by themselves. Okay, so when we do this, so we subtracted 2, in the blue one, we subtract 2 from both sides, right? When I subtract 2 from both sides, I get 3t is less than negative 9. Divide both sides by 3, t is less than negative 3. You guys agree with that? You sure? Okay. Now, if I do the yellow one, okay, so this yellow one, we're looking at, what would you do first? By 5. So I get negative 4t is less than negative 4. Now what do you do? Divide by negative 4. So t greater than 1, right?
No.
I know.
Okay. All right, so we get those two blue inequalities. T is less than negative 3, t is greater than 1. What was the original word that stuck those two things together? In the original problem, the word was or. Okay? So that word or should actually carry itself all the way through this, and when we're done, it should still be there in our answer. Does that make sense? Okay? So now I'm going to graph those two things individually. I'm going to graph t is less than negative 3. So what kind of dot does that give me? Open a negative 3 and graph which way? The left. Okay, and then we got that stuff there, right? The next one is t is greater than 1. So open dot 1, right? And we're going to graph to the right. And then when we want to write our final answer, t is less than negative 3, or t is greater than 1. We're going to put all this together. We put all of that one to be that, and all of that one, which would be that. Okay. When I think about these things, when I see the word and, obviously we've used the word overlap, right? Okay. When I see the word or, I think in my mind, in regards to graphing, I think the word both. Okay. Because in my final graph, do I have both of those things that we did in first and second number lines there? Can that make sense? Okay. So if you tie those words together, and give you an idea of what you need to do to complete those types of questions. Okay. I'll always skip this one for now. It's the same type of problem. I won't get down to this. It says compound inequalities. Compound inequalities that use the word and. This only works for and. You never do this with the word or. Okay? Can be written and solved in a more concise manner. Okay? This is only going to work sometimes, and it's when one side of your and statement, or one part, let's say one part of your inequality in your and statement. See how this is n minus 4 here? See how this is n minus 4 over here? See how that part of this inequality on the left and that part of this inequality on the right are identical? Does that make sense? When you have those identical components with an and statement, you can do what we're going to do. Okay? So we've got the word and I'm just going to highlight here that. What in the world?
What in the world? What in the world?
Okay, so that there and that there are identical, and they're stuck together with that word and. Okay? If this is the case, we can actually merge them together into one statement. So here's the idea of what's going on here. If I were to have -3 and -1. Okay, so if I had -3 is less than or equal to m minus 4 and m minus 4 is less than -1. Because those m minus 4s are the same, this is really what we're going to do. We're going to take this one, and we're going to merge the m minus 4s on top of one another. Does that make sense? And what are you left with? You're left with -3 less than or equal to m minus 4 less than -1. Does that make sense? Is that okay, Annika?
Yep.
Sure?
Yep.
All right. We'll have a quiz over this in the near future, not tomorrow. But I want to make sure, not over this, I want to make sure that you're good at this and not sticking pencils in your hair. Okay? So, since they both have that n minus 4, we can merge them together and we can get this -3 less than m minus 4 less than -1. Okay? And we ask ourselves, well, how do I solve that? Okay? If I were back up here, if I were looking at just this one right here, what would you do to both sides to solve for m? Add 4. If you were worried just about this one here, what would you do to both sides? Add 4. Okay, so in both those separate inequalities, you would do the same algebra, right? So let's look at it with one thing down here. If I'm going to try to get m by itself, don't I add 4 here? Does that make sense? And this here, that there is what I've got up here. Does that make sense, everybody? So you would add 4 to the m minus 4. You're going to add 4 to that, right? But isn't this here what I've got right here? Does that make sense? So over here, you would add 4 to both sides. So we add 4 here. Let's add 4 there. So we have a phrase like this. We have an inequality that's really got 3 parts. What you do to one part, you have to do to all 3 parts. So now if I start adding those, -3 plus 4 gives me 1. Less than or equal to m is less than -1 plus 4. 3. Okay? Now, think back. I'm just going to go back and just draw a comparison. If I had just these 2 things up here, if I had -3 less than or equal to m minus 4, you would have added 4 to both sides, right? We're giving you 1 is less than or equal to m. Is that what this says right here? Let's say 1 is less than or equal to m. Okay. If I'm doing the other one where it says m minus 4 is less than -1, you add 4 to both sides, right? M is less than 3. Does this right here say m is less than 3? Does that make sense to everybody? So doing it this way gets both of these done at the same time. Okay? So let's go a little bit further with this. Let's graph our solution. Okay? If I look at this, would you make the argument that in this structure, when I say 1 is less than or equal to m is less than 3, m is talking about our answers, right? M is all of our solutions. Would you say in that sentence, m is between 1 and 3? Right? You got 3 things up there, 1, m, and 3, and m is in the middle, right? And m is our solution. So 1 needs to be one of our endpoints of our solution here. 3 is the other endpoint. And this graph I'm going to actually too small for me. Let's do this. I'm going to say that this here, let's say that's 1. Let's go by 2. So there's 2. There's 3. So let's say 1, close dot, 3, open dot. But m is all the numbers that are between. So that would be all the numbers between. So that would actually be our answer. Okay? From 1 to 3, and shade in between. Now, what I want to do here is talk about how that structure, because m is the middle thing in 1, m, and 3. So it tells us graph 1 and graph 3 and then shade between those is exactly the same thing that happens when we graph these things individually and then look at where they overlap. So if I were to graph these things individually, there's the 1 number line, there's my second number line. Let's graph. This one here says m is greater or equal to 1, doesn't it? Start with the m greater than or equal to, and then my 1. This one here says m is less than 3. So here's 1, here's 2, here's 3, 1, 2, and 3. If I graph 1 is greater or equal to 1, if m is greater or equal to 1, close out there, shade that direction, right? If I say m is less than 3, open dot there, shade that direction, correct? Okay? The word that we started with was and, correct? And means overlap. Do they start overlapping at 1 and finish overlapping at 3? It gives me that blue result right there, that blue graph. Does that make sense to everybody? So when we want to write between statements, we call these between statements. Like if I say, let's go back up to the beginning real quick. When we say x is greater than or equal to 3, and x is less than or equal to 7. Okay? Well, let's put x in the middle. What number comes first, 3 or 7? 3, so I'll put 3 to the left. I'll put 7 to the right. In order on the number line, 3 would come first and 7 would come second, right? If I want to maintain that inequality sign is pointing to the 3, right? Let's make it point to the 3 here. Is this inequality sign pointing to the x?
Yeah.
Does that make sense? Okay. Now, so this statement here and that one there say the exact same thing. When you do this, when you write one like that bottom one, 3 is less than x is less than 7. When you write that, the number on the far left needs to be the smallest. The number on the far right needs to be the biggest. Okay? Now think about this. If we go through the same argument as before, if I wanted to graph this, don't I start at 3, start at 7, close out at 3, close out at 7, and x is in the middle, right? So don't I shade in the middle? Is that exactly what we got right here? Close out at 3, close out at 7, shade in the middle. Okay? So you have, when it's an and statement, you have options. That's what I'm trying to get at here. And they're going to bounce back and forth between the ways they present stuff to you. They're going to use the word and sometimes. Okay? And they'll say, x is greater than or equal to 3 and x is less than or equal to 7. Or they'll say 3 is less than or equal to x is less than or equal to 7, and you can get the same argument. Okay? So it's a notation thing that gets people confused sometimes because they bounce in and out of it. Okay? We have to realize the connection that they're the same. Okay? We'll practice a lot of this in the next couple days, guys. I wanted to get, just in terms of time, okay, I wanted to at least get this